Hello, fifth graders. Another early video for fifth grade. And we've already established the definition of exponents, what an exponent is. And so it's not too early by any means to introduce you to some numbers that are going to play a big role in future math courses, because that's what I'm always trying to do, is make the math relevant. We have limited time. Even though we have class time, we have 180 school days. I can communicate with you with these videos. You can be watching them at home. So in one sense, I try to make as much time as possible, but it's still limited. And so we have to be choosy, and we have to try to only do math that will be relevant in the future. This will definitely be relevant in the future, and yet, once again, very simple concept. If you know your multiplication tables, you can understand these so-called square numbers. They go by at least two different names: square numbers and perfect squares. This abbreviation here, AKA, stands for also known as. That applies to people. For example, there's an actor named, I think his name is Dwayne Johnson, but he's AKA, also known as The Rock. And there's also three letters FKA, which means formerly as in the past, formerly known as. So if somebody changes their name, gets married, gets a new last name, you can say Mary Smith, formerly known as Mary Jones. So there are two culturally relevant things. Again, you know, if I introduce you to something that's not math, also I'm striving to introduce you to things that will come up in the future and make it easier for you to make meaning and understand the world and how we communicate. Something I'm always striving to do in math is to make connections between let's say the arithmetic or the algebra, the numbers, and geometry. And we're definitely going to make in this video a connection between the numbers over here and geometry. And this video will explain why the exponent of 2 is called squared. So over here in this column we have the first 11 whole numbers. From 0 to 10 is 11 numbers, and they're just going to be n. We frequently use n in math to stand for numbers. No surprise there. N is a very commonly used letter, which is standing for a number in math. And over here we have n squared. Now in the future I could just stop there, n squared. You know now, you should know forever what that means. But I wrote it here to remind you, it means n times n. And when we put the two n's right next to each other, it means multiplication. And I wrote it the old way, n times n. You can easily fill in the right column of this chart. 0 squared, 0 times 0 is of course 0. 1 to the 2 power, or 1 squared, 1 times 1 is 1. 2 squared, 2 times 2 is 4. Now, I think I talked earlier about exceptions to the rule. Now, let's just recall this. 3 to the 2 power does not equal 6. 3 squared, or 3 to the 2 power, is 3 times 3, or 9. Now here, you might think when we have 2 to the 2 power, that does equal 4, but don't make this mistake of thinking that you can do 2 times 2 to get the 4. It just so happens you can here, so you've got to be careful. This does mean 2 times 2, which is 4, but with 3 squared, it's not 6. Please make sure you understand that. Here's the 3 squared right here, not 6, but of course 9, 3 times 3. 4 squared, we're going to call it that, 4 to the 2 power. We're usually going to call it 4 squared. And of course it is 16, 4 times 4. 5 squared is 25. And again, you should be able to get all of these very easily if you know your single-digit multiplication facts. These may even have been emphasized by your earlier teachers. Sometimes earlier teachers, when they're teaching either addition or multiplication of single-digit numbers, they'll talk about doubles. Doubles. Now, in my view, I'm not talking about the teachers here at St. John's, but in general, all lower grade teachers, personally, I think they might overemphasize that idea of doubles, because sometimes they'll take this approach. Well, 4 plus 4. 4 plus 4, that's a double. Of course, it's 8. Now, the nice thing about 4 plus 4, the thing about doubles, which is useful for the future, when a first grade teacher is teaching 4 plus 4 and calling it a double, and then maybe a 6 plus 6, a double, you make a connection, you make a leap there to multiplication by realizing that 4 plus 4 is the same as 2 times 4. When you add 2 4s, it's 2 times 4. So there is some importance to doubles. Sometimes teachers will, in my view, overuse the concept of doubles. For example, let's say you assume you know that 5 plus 5 is 10. Well, 4 plus 4, another double, or let's say 4 plus 5. 4 plus 5. So the teacher assumes you know 5 plus 5 is 10. So 4 plus 5 has to be 1 less than that double. The doubles are kind of used as benchmarks or markers along the way to then learn other single-digit addition facts. But in my opinion, you should just know 4 plus 5 is 9, memorize it on its own without having to refer to doubles. In terms of doubles with multiplication, if a third grade teacher emphasizes, well, these doubles are important, and again, the third grade teacher could say, all right, if you know, let's say 5 times 5 is 25, then you could reason from there that 4 times 5 is 5 less. 20 is 5 less than the 25. So I suppose those doubles with multiplication could be benchmarks to help you learn some other facts. But again, in my view, you should independently just memorize, get into your long-term memory that 4 times 5 is 20 without having to refer to the double of 5 times 5. Now maybe this plays for it early on, but eventually you should learn those individual facts on their own. Okay. So that's just this. You may have, in 3rd grade into 4th grade, you may have seen these as special, a number times itself. And that's good to learn that early on, because it then leads to this. And square numbers, a number times itself, or a double with multiplication, is very relevant to the future. All of these numbers are going to be extremely relevant to the future. My 8th grade Algebra 1 students, when they see 25, they need to know instantly that it's 5 times 5 or 5 squared. You go backwards from these as well. We can't do everything at once, but there's a symbol and a concept for going from this column back to that column, and it's something known as square root. But again, we can't do everything at once. 6 squared, or 6 to the 2 power, is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. Now, this chart with n on the left and n squared on the right is infinite. Just as you can go infinitely with the whole numbers, each one of those whole numbers has a square, the whole number squared, and so this column goes on forever as well. You should absolutely recognize all of those n squareds there. You probably already have, with this idea of doubles from 3rd grade. If you don't recognize them right away as being special, please do that. Do that as soon as possible. Now comes the question of which others beyond here should you know, should you memorize? And that's an individual question. For me, I have memorized many others beyond this simply because I've been doing it so long and they come up. sometimes the textbook authors will expect you, for example, to recognize 13 squared. Well, 13 squared is perhaps the first one that we get to that we have to work at. But, you know, since the textbook authors sort of have this habit of putting it in there every now and then, eventually you just come to know it. Let me pause here and extend this chart a little bit, past 13, and look at some other ends here. We're not going to look at, you know, I'm going to skip around. Can't look at all of them because there are an infinite number of them. But I'm going to sort of skip around and give you an idea of some of the ones you should recognize beyond the first 11. So what I've done here, since I've run out of room at the bottom, I've just put another table next to the one that's there before. So I've got a new n column, which continues from the 10 to 11, 12, 13, and so on. And then a new n squared column going along with the n column next to it. Well, I mentioned 13 squared before. It's sort of it's interesting in terms of how the game is played. In many of the textbooks that I've used through the years for 8th grade Algebra 1, and maybe even in a 7th grade textbook, 13 squared is kind of something you're expected to know. 11 squared, many of us, including myself years ago, learned the multiplication facts up to 12 times 12. See, really only the single-digit multiplication facts are essential, going up to 9 times 9. But going into the tens is very easy. 3 times 10 is 30, and 9 times 10 is 90, and so on. So the tens are easy to memorize. 11s as well. 4 times 11 is 44. 9 times 11 is 99. You get up to 11 times 11, 11 times 11. That's 121. Kind of something that's expected sometimes to be known because of this tradition of learning from 1 times 1 all the way up to 12 times 12. That was a tradition and still is in some places. 11 times 11, 11 squared is 121. And then this one here, 12 squared, 12 times 12, it is 144. Now, maybe one of the reasons that there was this tradition of learning the times tables up to 12 times 12 is because dozens are very common in commerce still to this day. You buy, the most obvious example is eggs. You buy eggs by the dozen. So if you buy 4 cartons of eggs, 4 dozen eggs, it's nice to know that it's 48. And there was also this tradition in commerce, in the buying and selling of things. I think it's less popular nowadays than it was before, but since things were sold in dozens, it became sort of popular to talk about 12 dozen. What if it's kind of interesting, you know, from a math point of view, it's 12 squared, 12 times 12. It happens to be 144, and a name was given to that. A name is given in commerce to the number 144, which is 12 dozen. It's called the gross, G-R-O-S-S. It's kind of like the word that used to be popular for when something is like unpleasant, gory, or, you know, something looks messy, we call it gross. So there's actually a little pun on that I'll try to remember to introduce to you. Well, let me do it now. I'll do it now. So 12 squared is 144, and it's often referred to as a gross of something, 12 dozen things. Well, here's the little joke which puns on that word gross, G-R-O-S-S, and it's 2 meanings. It actually has more than 2 meanings, but we'll just focus on 2 of them. And the little joke, the little pun goes like this. Why do we not use the number 288 in math class? Can anyone think of the answer? Why do we never use the number 288 in math class? Well, the answer is, it's too gross. It's too gross to use. Well, one of those puns is that. Like, it's too disgusting It's too disgusting to use. But we're also punning actually on both. We're punning on these two twos, and we're also punning on the two meanings of gross. So 288 is 2 gross, or 2 times 144. So there's my eye-rolling math joke for today. I don't put one in every video, but couldn't resist here, sorry. And in terms of puns, that's how I roll. That's how I roll. And there's another one. If you don't get that, ask somebody. All right. So let's get away from the eye-rolling puns and back to the table of squares. We can call this a table of squares, a table of square numbers, or perfect squares. And this one here, see, it's kind of popular in the textbooks because people don't typically memorize up to 13 times 13. They may have up to 12 times 12. So the textbook, let's try to get people to learn a new one, I guess, is their motivation. But 13 squared is 169. I've kind of memorized a few more of these just because they kind of come up now and then, just through years of experience. It's not that I'm brilliant, it's just that I've done this more than you have. That's an important message for any teacher, that yes, we're authority figures. We hope that that you try to emulate or copy the positive things that we express to you. We're not perfect, so you shouldn't copy everything that we do, but to a large extent, you should. That's how we learn from parents and later from teachers. But it's also important to realize that this knowledge that I'm trying to impart to you through hoping that you'll sort of imitate my love for math and my approach to math, it's possible for you. It's very possible for you. And it's just don't think of, I'm way up here and you're way down there. That's only an accident of birth. It's only because I was born in 1958 that I'm up here now. You're going to be there. You could be there at a much younger age. You will be there at a much younger age than I am now, with learning and understanding and enjoying a whole lot of math. Now, I arbitrarily jumped from 15 to 20. 16 squared, 17 squared, 18 squared, if you need them, you can work them out here. You might want to verify, do 15 times 15, use the standard math multiplication algorithm. 15 times 15 is this, 14 times 14 is that. Now this one you should easily be able to do mentally. 20 squared, 20 to the 2 power. It's not 40, it's 20 times 20, so it's 400, right? This is 400. And in an earlier video, we talked about how easy it is to multiply numbers like 20 times 20. 2 times 2 with 2 zeros tacked on. And 30 squared is, of course, 900. And notice that when we are looking at numbers like this, we're just building on the earlier ones. This is 900, not 90, 900. 30 times 30 is a 9 with 2 zeros after it. About 100 squared. 100 times 100. Well, it's going to be a 1 followed by 4 zeros. Now, you may remember from a previous video, that result, which is 10,000, is 10 to the 4th. Now, there's actually a very important concept here that I'll just briefly introduce you to it now. 10 squared times 10 squared is 10 to the 4th. What we're actually doing here is we're adding these exponents. Now, it is true that 2 times 2 is 4, but in this context, it's an addition. And it's easy to understand. 10 squared is 10 times 10. This 10 squared is also 10 times 10. And we're multiplying, so what do we have? We have 4 tens multiplied together, which is 10 to the 4th. 100 times 100 squared. Okay, so 100 squared is 10,000. It's 100 times 100. But it's not a coincidence that that is also 10 to the 4th power. Not a coincidence. 100 squared is 10,000. Now, how about 150 squared? This was kind of arbitrary. These rest of these, they're all arbitrary, just trying to give you some sense for how this will work, and don't be intimidated by it. Well, if you know that 15 times 15 is 225, and that is something that you might sort of memorize as time goes on. 15 times 15 is 225, but we're multiplying 150 times 150, so there'll be 2 zeros tacked on to this, right? So 150 squared, or 150 times 150, is 22,500. Now notice how big that number is. When we square numbers, it doesn't seem too wild over here, but once these n's get bigger, the n squareds get very big. This is why we call them powers. The exponent is very powerful. Now 200 times 200 is easy. 200 squared. 2 squared is 4, but then we're doing 200 times 200 for a total of 4 zeros. So this will be a 4 followed by 4 zeros. And one thing we can do to just, check the reasonableness of our answers, all of these numbers are getting bigger over here. If I left out a 0, made that mistake, I could maybe catch it over here, because if the numbers aren't going up over here, there's something wrong, because the n's are going up. They all look pretty good, all right? And 500 squared, 500 times 500 will be a 25, 5 times 5, followed by how many zeros? 4 once again. So a 25 followed by 4 zeros would be 250,000. Now notice the big jump there, okay? We may not think of from 200 to 500, I guess that's kind of a big jump, but to me over here, this even seems like a very big jump, going from 40,000 to 250,000, but it's correct. I believe all of this is correct. And please make sure that you agree with that, either mentally or multiplying the numbers together with the standard algorithm. We'll pause there for a moment. This final portion of this video is more along the lines of why. The earlier, the how, just understanding the meaning of the exponent. That little 2 means multiply the number by itself. This was all self-evident to you, right? How to get to them if you know how to multiply numbers. There really wasn't much why there. There was just the introduction of that symbol of the exponent of 2, or the squaring of the number. Well, the link here to the y, and also the y here is the connection between the math or the arithmetic and the geometry, is right in that word square. And I'd like to ask this question over here. Which number is special? I'll put that in quotation marks. That's a very vague word. That's not a word I'm going to use a lot in math. I'm not going to define anything with the word special. See, the word special, the best way to answer this, which is special, 49 or 50, the only way to really answer that is it depends. It depends what you're looking at. Depends maybe how old you are. Well, very young people, I think, are going to almost unanimously say that 50 is special. Why? Because it's a multiple of 10. The multiples of 10 are special to us when we're young. Learning how to count by tens is valuable. It's something that's in the math mind of the first grader and the second grader. 49, not so much. Also, the 50, the 50 is half of 100. 100 is an important number. 100 cents in a dollar. Later on, we'll learn that the number 100 is very special, very important to us in the definition of percent. What does percent mean? Keep in mind, keep that in the back of your mind. This year, we're going to define what percent means. You already have some concepts of percent, and I probably won't change those ideas. The ideas that you have of percent already are probably okay, but I'm going to start from the very beginning with a definition. What is a percent? You may know, for example, that 50% is half, and that's because 50 is half of 100. That is true. And we're going to see why, really. We're going to look at the why behind that. But to a young person, I think it's safe to say 50 is more special than 49. But for our purposes, and the fact that 49 is right here at 7 squared, just for our purposes, we're going to say that 49 is more special than 50. It's done. And one way to answer that is 49 is on this list of squares and 50 isn't. So let's now get into this idea of square from a geometry point of view. There is one square. Forgive my drawing here. I'm going to do the best I can to make things that look like squares that are all the same square, congruent squares, squares that are the same size. I'm going to be constructing a whole bunch of those, and I hope they look okay. But there's one square, and here's one right here. You can make a square. Okay. It's a very subtle, very complex idea. Make sure you pay close attention. You can make a square with one square. Okay. All right. But can you make a square with two squares? Two identical squares. Or three squares? You cannot. The next square you can make that is made of more than just one square is a square that's made up of 4 of the smaller squares. So maybe I'll use alternating colors. Okay, now right now we have 3 squares, but we have a little square missing here, and that's going to be a pattern. Right? We have a square missing right there. We have to fill in another one. So what do we have now? We have a 2 by 2 square, right? There are 2 squares this way and 2 squares that way. 2 times 2 is 4. 4 is our second square number. And by the way, I skipped 0. You can't make a square with 0 squares, but 0 squared is 0. But okay? Do you realize that I could not make a square with 2 squares or 3 squares? I had to go to 4. And to sort of build a bigger square on this one, 5 will not work. Let me put a 5th one here. Now, you can't even make there are 5 total squares there. I'm going to alternate colors so you can see how it grows going forward. You can't even make a rectangle with 5 squares other than 1 by 5, right? 5 squares lined up in a row, horizontally or vertically. That's because 5 is what we call a prime number. It doesn't have any factors other than 1 in itself. Now let's go to 6. Now that's not a square. There are 6 squares there. That's not the big thing is not a square, it's a rectangle. And notice it's 2 by 3, because 2 times 3 is 6. 6 is not prime, so you can make a rectangle other than 1 by 6. Other than 6 squares lined up in a row, you can go 2 rows of 3, because 6 has the factors 2 times 3. We associate in 3rd grade multiplication facts with area of a rectangle. 2 times 3 is 6. But it's not a square. So let me keep building. Let me put 2 up here. And notice I'm building by putting squares on the 2 of the sides before. Right? I put 2 red squares here and here, then I had a space to fill in. Now we've got the big square we have the 2 by 2 or 4, so I put 2 squares up here on this side, and 2 squares here on this side, but again I have that space to fill in there. Now how many squares are there right now? Count them, there are 8. I cannot form a square with 8 squares. If I took these 2 and moved them down here, it'd be a rectangle, because 8 is 2 times 4 if I move them down here, but it's not a square. When I fill in that space, and there will always be that space there, now we have a new square. And how many little squares are there? 9, of course. There's the 9. And notice, there are 9 total squares. There are 3 going this way, and 3 going that way. This is why we call 3 times 3, 3 squared. This is why 3 to the 2, which is 3 times 3, or 9, this is why we call it squared, because when you have a square where each side is 3 units long, the area of the big square is 9 square units. 1, 2, 3, 4, 5, 6, 7, 8, 9, where each of those original squares was a unit, or a square unit, a unit of area. So this is an explanation. Let's go one more, and you know what the next square number is. You know what the next biggest square is. Now I've got a square using 9. Well, I'm not going to get a square using 10 squares. 10 is not special for our purposes. Sometimes 12 is considered special for young people. When you're in second, third grade, 12 might be a special number because, well, it has factors. It's 1 times 12, it's 2 times 6, it's 3 times 4. So 12 is a number you deal with a lot when you're young and you lose learning the multiplication facts. But you cannot make a square out of 12 squares. You've got to jump all the way from 9 to 16. Let's see how that jump works in terms of building this bigger square. Remember how it works. Now we have 3 going this way and 3 going this way. Let me put a square on the 3 here and the 3 here. So alternating colors, so I'll go to red. So a square there, there, and there. That's 3 more. And then down here I build a square here, here, and here. That's also 3 more. But when you build squares on those previous sides, you're always going to have that one square missing there that you have to fill in. There's a square that is 4 by 4. Okay, 4 by 4. And in third grade, you knew that a square 4 by 4 had 16 squares making it up. We think of multiplication as the area of a rectangle. Well, a square is a rectangle. It's a special kind of rectangle. It's that double. It's 4 times 4, giving you the area of 16. I guess we'll go one more. This can continue forever. Let me go one more, building a bigger square. And 20 is not going to work. 24, you might think, well, 24 is a nice number. Well, it is for some purposes, but not here. The next nice number for us, the next square number is 25. 1, 2, 3, 4. There were 4 squares on that side. And do the same thing over here, 4 more squares. So now I've got 4 for 8. But we've got that missing square up there in the corner to add that. Now we've got 5 this way and 5 that way for a total of 25. Okay? Now we're going to close here with a very interesting observation about square numbers. The square numbers are sums of the odd whole numbers. Every square number is a sum of the first certain number of odd numbers. All right? Let me kind of give you an indication of that over here. When you go from, let's start with 1, let's start with 0, we can start with 0. When you go from 0 to 1 here, you're adding 1. Right? When you go from this 1 to this 4, what are you adding? When you go from this 1 to this 4, you're adding 3. When you go from 4 to 5, notice a pattern. You're adding 5. When you go from 9 to 16, what are you adding? 7. Right? And when you go from 16 to 25, you are, of course, adding 9. Make sure you agree with all of those addition facts there. Okay? 1, 3, 5, 7, 9. This pattern will continue forever. When you go, I didn't show it over here geometrically, but when you go from 25 to 36, of course, that's adding 11. When you go from 36 to 49, that is adding 13. So you might say that when you're, you might just say, well, this is an oddity. This is kind of interesting. But you can go beyond that and understand why it must be true with the geometry. So look what happened over here. I started with no, then I started with no squares, then I added the 1 to 0 and got the first one that I had there. Now, how did I get from the 1 squared to 4 squares. I added those 3. Remember, I literally added those 3 squares to this one to make the new square. That's this plus 3 going from 1 to 4. And then to the 2 by 2, to the 4, I added 5. Remember, it was 2 and 2, but then the little extra corner one up here, that little extra corner one makes the number you add odd, because you're adding 2 and 2, and then 1 more. That's odd. That's this 5. And then when you go from the 3 by 3 to the 4 by 4, you added 3 here and 3 here, but also the extra one in the corner for a total of 7. So these squares that you added here were this plus 7. When you went from 9 squares to 16 squares, you're adding 7. And the last one that I showed went from 16, we had 16 here, it says red on the outside red here. That was 16, 4 times 4. And then I got to 25, 5 times 5, by adding 4 here, 4 here, plus the one in the corner, makes it 9, that's this plus 9. So this last thing that I'm closing with is, it's a general experience we have in math where very often a pattern that we notice, there's a why to it. And in this case, this arithmetic pattern of adding 1, adding 3, adding 5, and so on, had a geometric interpretation to really drive it home in our minds as to why it's true. So we'll close there. Hope you enjoyed this, and there are many more steps along the journey. I'll try to make each step an easy one, a small one that you understand fully, and then all these little steps you make are building the structure of math that you will succeed in and enjoy even more when you're older. Bye-bye for now, 5th graders.